There are two functions up on the board here. I've got f of x equals x squared, and g of x equals the absolute value of x. Now both of these pass through the origin, and both of them achieve a minimum value, a lowest point on the graph at the origin. But they do that a little bit differently. You'll notice this is a nice, smooth, rounded change, whereas this is a much sharper corner. Okay. In both cases, we're at this minimum value because that's the place where the graph stops going down and then starts going up. Same thing over here. We're going down until we hit the origin, then we're going up as we move away from that. So the graph changes its behavior at that location. So it's kind of interesting to take a look at what is the derivative or the slope of the tangent line at those points. And we'll be seeing a lot of this semester because as we learn more calculus, one of the applications that we'll have for that is to find the location and the value of relative maxes and mins of functions. Now, in some cases, like with x squared and the absolute value of x, we're familiar with the graphs, so we already know where they are. But there are a lot of functions where we might not be familiar with the graphs, and calculus will enable us to find those locations. Now, if I think about what the derivative could be, the first thing I would do is say, is my function going up or down as we pass through this point? Well, it's where we stop going down and start going up. So we're not really doing either at that point. But if we were going up, that would tell us that the derivative, or the slope of the tangent line, should be positive. And if we were going down, that would tell us that the derivative, or the slope of the tangent line, should be negative. If the answer is we're not really doing either one of those things directly at this point, that tells me that the derivative shouldn't be positive or negative. Now there are two possibilities. I'm going to encourage you, if you can't think of what they are, to just pause the video. I'm just going to do this one very informally. Pause the video really quick. See if you can think of what those possibilities are. Welcome back. Okay. There is one number that is neither positive nor negative, and that is 0. So one possibility is that the derivative, or the slope of the tangent line, to one or both of these graphs at the origin would be 0. Now that would mean the slope is 0, so that would give me a horizontal tangent line. The other possibility, now 0 is the only number, only real number that is not positive or negative, so the other possibility is that the derivative simply does not exist. That there is no line, no non-vertical line that best approximates what the function is doing as it passes through the origin. Now I mentioned that these two functions have very different behavior. They both have a minimum, but here it's nice and smooth and rounded, and here it's a sharp corner. That might make you suspicious that we've got sort of two types of behavior and two possibilities for what the derivative could be. Maybe one of them goes with one and the other with the other. What I want you to do is make a guess by filling out a table of values. So I've got the same table of values beneath each question here. We're looking at the point where the x value is 0. So in the first two columns, in the very first column, I filled in a sequence of x values that are smaller than 0, so they're negative, so they're coming in from the left, but they're getting closer and closer to 0, and I want you to calculate the slopes of those secant lines. And then the next two columns, I've got another sequence of x values, but these are positive x values. So they're coming in from the right, but they're getting closer and closer to 0, and I want you to calculate the slopes of those secant lines. So you're going to calculate these 6 slopes, and you're going to say, is there a pattern? Are these slopes approaching a number? Are these slopes approaching a number? And if so, is it the same number? If so, that's what you're going to guess for the derivative. You're going to do exactly the same thing. Whoops, I forgot to fill in my x values. Let's fill those in really quickly. You're going to do exactly the same thing over here. Same table of values, but this time you're working with the absolute value function. Now, for each of these tables, you can either, if you want to, just calculate the 6 slopes individually by using rise over run. It may make sense to find a formula for the slope function, this m of x function, using the origin and an arbitrary point. So here, an arbitrary point would look like x squared, and here an arbitrary point would look like x absolute value of x. By saying that's an arbitrary point, I say that I could use that same name for any point on this parabola other than the origin, of course, because I want it to be my second point. That's particularly important here because x does not mean that x has to be positive. I could use that same name for a point on the left half of the v. So you may want to go ahead and find a formula for m of x. After we make a guess based on this table of values, we will calculate the formula for the m of x, the slope of the secant line function, graph that function, and try to confirm that the guess we make based on this table of values is correct. All right, so go ahead and pause the video. I'm actually going to edit so that I can fill in the tables while you're doing that, and then start the video again, and we'll resume, look at the tables, and make our guesses. I filled in both of these tables here. Now, for this first graph, I found it helpful to actually calculate the formula for the slope of the secant line. It would just be rise over run, so that's x squared minus 0 over x minus 0, which I have here. Of course, that just means it's x squared over x, and I can cancel a factor of x. So we simply get x, but with the restriction that x isn't 0. And again, that restriction has an algebraic interpretation. We had an x in the denominator, and we know we can't have 0 in the denominator. It also had a geometric interpretation. This point x squared was meant to be a second point. It couldn't be the same as my first point because then I wouldn't have two points, and I need 2 points to create a secant line. Okay, but none of these x values were 0, so it turned out that the slope of the secant line in each case simply matched the x value of that second point. Now, since we'd chosen our x values so that they were getting closer and closer to 0, we definitely have that the slopes of the secant lines are also getting closer to 0, both as we come in from the left of 0 and as we approach it from the right. So, we could guess in this case that the slope of the tangent line, now I'm still going to put a question mark here because this is just a guess, but this would be a guess that's supported by evidence. We would guess that it is equal to 0 here. Now, for the absolute value function, I actually didn't find at this point a formula for the slope of the secant line because I think it was easiest to do it just visually. Notice, if I'm choosing 0, 0 and a point on the left half of this v, the secant line is just the infinite extension of this left half of the v. That's a line of slope -1. So for all of these points on the left, I'm getting exactly the same secant line, and therefore exactly the same slope, and it's -1. On the other hand, over here on the right-hand side, the secant line is just the infinite extension of the right half of the v, which is a line of slope 1. So all of the slopes that we get here are 1. Now, we definitely have patterns. As we get closer to 0 from the left, the slopes are all -1. As we get closer to 0 from the right, the slopes are all +1. So, do I have a unique pattern? Is there one number that we're approaching? Because if I'm looking for the slope of a line can only have one slope. And the tangent line, if it exists, is unique. A curve can't have 2 different tangents at one point. Okay? Tangent line is the line, if it exists, that best approximates a function at a point. I don't see the same pattern here. So my best guess would be that the slope of the tangent line, I'm going to just write DNE, and that stands for does not exist. Okay. So my guess is that we've got 0 as the derivative, or the slope of the tangent line here. Now that would mean that the line that's tangent to the parabola at the origin would actually just be the x-axis. It would be that horizontal line. And over here, we're saying there is no one line that best approximates the function at this point. That would include that the x-axis doesn't approximate the function. Now, that looks like a good guess to me. Notice, if I follow this curve, sort of tracing it with my hand, as I pass through the origin, I level out, and then I start going up. I can do that smoothly moving along the curve. Here, there's no leveling out. I'm not getting less steep and less steep until I'm at 0. I sort of have to pick up my hand and put it back down at this new slope to move up. Okay. So it does look like nice, smooth, rounded changes are going to have a derivative of 0. Abrupt changes that give me a corner, or it would also be true if I had something like this, which we call a cusp. Abrupt changes are going to give me that the derivative doesn't exist. I think that's suggested by the evidence. But let's actually now prove that we're right, at least in these two cases. So I'm going to have you pause the video again, and what I want you to do is find a formula for m of x, which is the slope of the secant line through an arbitrary point and the origin. I want you to do that for both graphs. I'm going to just recycle the name m of x, but it'll be a different formula when it's secant to the parabola and when it's secant to the absolute value. I want you to find and simplify that formula and then graph m of x. You should be able to simplify it until it's a function that you know how to graph. Graph it and then come back and we'll talk about it. So pause the video again, find and simplify these formulas and graph them. And then we'll talk about how that confirms, or doesn't, but hopefully it will confirm the educated guesses that we just made. For the graph of y equals x squared, we had already actually found a formula for m of x. It was just x with the restriction that x wasn't 0. Okay, so m of x, that's the function y equals x, except there's going to be a hole at the origin. Y equals x would just give me the line of slope 1 through the origin. We remove the point that would be there if x were 0. So here, I can look at this graph, and now this graph consists of infinitely many points. And so I know that here we're getting arbitrarily close to where x is equal to 0. And I can see, as I move in along this graph, coming in from the left, my y values, or my m of x values, are approaching 0. Same thing as we come in from the right. So here, this graph confirms, so now this is no longer a guess. We know that the slope of the tangent line at 0 is 0. There will be a horizontal tangent there. Excellent. Now I'm going to erase this just because I'm going to need a little bit of space here in order to explain my work for the absolute value function. So here, I hadn't previously found a formula for m of x, but it's just rise over run. So it would be the absolute value of x minus 0 over x minus 0. Which of course is just the absolute value of x over x. But now I need to simplify that, and you can see I broke it up into a piecewise function. That's because the absolute value can be written as a piecewise function, because there are really two different rules. If I plug in a positive number, or 0 for that matter, to the absolute value function, I just get out the same thing I plugged in. So the absolute value of x is just going to be x. It's going to match the input, and that's true if x is bigger than or equal to 0. But if I plug in a negative number, like if I try to take the absolute value of negative 5, I don't get negative 5. I get 5. I get the opposite thing. So I'm going to get the opposite of x if x is less than 0. Now, a lot of times students do not like that because they say, wait, absolute value can't be negative. That's not negative. That's the opposite of x. And I only use that rule if x is a negative number. The opposite of a negative number is a positive number. So this does represent something positive. So very important to recognize with numbers, I can look at that and I can say that is a negative number. And you know how I know? There's a negative sign there. But with variables, I can't do that. I can't say that the presence of a negative in front of a variable makes that value negative. It just makes it the opposite of whatever the variable was. Okay. All right, so I used this rule over here. So I said the top of the fraction will simplify to be just x, and that will be if x is positive. Okay. Now, I didn't include 0 this time because 0 would not be in the domain because I have x in the denominator. Okay. And then I said, if x is negative, the top of this fraction would simplify to the opposite of x. So we would get the opposite of x over x. And of course, as long as x isn't 0, x over x is just 1, and the opposite of x over x is just negative 1. So that confirms what we had seen visually last time, that anytime we chose a number that was negative, so that we were to the left of 0, we were getting the slope of the left half of the v, which was negative 1. And anytime we chose a number that was positive, so that it was to the right of 0, our secant line was just the extension of the right half of the v, so it had slope 1. So we're getting this function that always takes on one of two values, 1 or negative 1. Now if we graph that, here you can see we're at a constant height of negative 1 to the left of 0, and then we jump up to a constant height of positive 1 to the right of 0. So if I follow this in, coming in from the left, I'm expecting there to be a point here whose m of x value is negative 1. Coming in from the right, I expect there to be a point up here whose m of x value is positive 1. That's not the same. So there's not a unique number that the slopes are getting close to, and so now this was a guess before, now I know it's right. The slope of the tangent line does not exist at the origin for the absolute value function. And so that generalization that I suggested previously will hold. If I have a nice, smooth, rounded change where my graph changes direction, in this case from down to up, but it would apply for up to down as well, then I'm going to have a horizontal tangent. The slope of the tangent line will be 0. If I have a sudden change, either a corner or a cusp, then the tangent line doesn't exist, therefore its slope doesn't exist, therefore the derivative doesn't